Hi everyone, welcome to section 1.4 where we're going to talk about one of the most important objects in geometry, and that's an angle. Angles we'll see a lot this year in geometry honors. And an angle, basically what we can do is we can just take these two friends that we already have in geometry. Remember what these are? They've got an endpoint on one side and they go through the next point and form an arrow. These are called rays. So what I'm going to do is I'm going to take one ray, I'm just going to literally paste him over here. You see how they both have B's on it. So I'm going to take this ray of ray BA and I'll put it right here. And look what I find. I find what's called an angle. This is an angle, folks. An angle is formed by two rays that are connected at a single point B here, which would be called our vertex. And so we can have an angle of any different size that we want, and we'll have different names for all the different types of sizes that we have for angles. So this is an angle, and we're going to call it now by the three letters that you see here. We have A, and we have B, and we have C. But it does make a difference in which order in which we say it. We're going to always make sure the vertex is the middle letter when we say the angle. But make sure the vertex is the middle angle. So for example, this is angle ABC. Now right now, just as I wrote it, if I just wrote those three letters, that looks like a plane. So we have to signify that this is an angle by doing a little mini angle symbol in front of it. That's angle ABC. Okay? Or I can also call this angle CBA because the vertex is still in the middle. But can you see, I can't call this angle BAC because A is not the vertex. So we're not going to use that. So the only two ways to call this guy would be angle ABC or angle CBA. But there's also a couple other ways to say it too. Over here in this diagram, we have a whole bunch of angles. Can you count them up? We actually have three of them if you can see them. We have the one on the far left, which we can call angle AX is the vertex, B. Or we can also call them angle BXA is totally fine. But also, do you notice that there is a little number here inside the angle? We can also use that number as a reference for the angle. So this angle can also be called just angle 1. And that's all the same angle. How about over here on the right side? This little guy here, we can call him, let's see, by letters, it'd be angle BXC or angle CXB. Or, again, you see the number there, so this could just be angle 2. Great, but I said there were three angles, right? Where's the third one? Did you see it? The full one all together. This one, the whole big one, is angle AXC or angle CXA. But we can't really call it angle 1 and 2 because that doesn't quite make sense. We don't have a number for the big, larger angle, so all we have are those two choices. So we can label them by three letters and always have the vertex as the middle letter. Or if there is a number inside, we can use that number as a reference for the angle as well. We like to measure angles a lot using a very old-fashioned device called a protractor. Some of you have seen it and used it before. And it's kind of nice because if you look at a protractor, it's sort of like a half circle here. When you put it on top of an angle to measure it, you've got two sets of numbers here on a protractor. You have one going from 0 to 180 degrees that way. But then also on the inside you have again 0 to 180 this way. So depending on where you put your angles, you can measure them any which way you want using a protractor. So for example, if I look at, how about this angle here? How about angle WOZ or ZOW? Notice that here he's right on the edge when I'm at Z, so that's at 0, and I would count going up this way. The other numbers wouldn't make sense because it'd be going backwards. If I go up this way, I'd be going 0, and I stop right about at about 45 degrees. So I think I travel an entire 45 degrees. And degrees are a very, very popular way of measuring angles. Very popular unit. If I want to go way over here on the other side and maybe do this angle here, this would be angle XOY. And I can say angle XOY. And how much is it measured? I'll put M. M, the measurement of angle XOY. Well, let's see. I'm not going to use the inside numbers now because they go backwards. We want to go forwards. So I'm starting at 0, and I go all the way to, looks like 40 here. So I traveled a whole distance of 40 degrees. So the measure of XOY was 40. And over on the right-hand side, the measure of angle, WOZ, was 45. Now those were both pretty easy, right, folks? Because they were sort of on the edge here, so it's easy to measure. But what if they're maybe inside here? How do we do that? That's a little tricky. We'll come back to that in just a sec. Let's name some of these angles. Well, depending on how big they are, we can have something like an acute angle. An acute angle measures between 0 degrees and 90 degrees. For example, if I have an angle here, that red angle here is between 0 and 90. As you see, using the inner numbers, 0 up to about, it looks like maybe about 42 or so. That's an acute angle because it is smaller than 90 and bigger than 0. Or how about a right angle? A right angle is exactly at the 90 degree symbol. For example, right there. That is 90 degrees. That's a right angle. Exactly 90 degrees. Okay, we've got less than 90, we've got right at 90, and we go bigger than 90, we get what's called an obtuse. Obtuse angle is going to be bigger than 90, but less than the full 180 that you see here on the protractor. So how about something like this? I'll take it from this side, and I'll draw it bigger than 90, and I'll go maybe over here. This whole angle right here is bigger than the right angle that you saw in blue, but it's less than the full distance all the way around the protractor there. So that is an obtuse. But what if we go all the way? If I did go all the way, and I started on the right-hand side here, and I went all the way to the end, and I made this side over here, that's a full 180 degree angle. That's called a straight angle. Makes sense though, doesn't it? You look at it straight because what does it form? Basically just a straight line. So these are the 4 types that you have. Acute is between 0 and 90. A right angle is exactly 90. Obtuse is between 90 and 180. And a straight angle or a straight line is exactly 180 degrees. Great. But now, what can we do to sort of add and put together angles? We had before the segment addition postulate, which said if you can add 2 parts of a segment together, you'll get the larger segment. So believe it or not, we actually have a postulate for angles that do the same thing. This is called the angle addition postulate, which says, if you look at the diagram over here, friends, if I've got a point B that's on the interior of an angle, interior being like on the inside or inside the mouth, then I can form another angle going through the point B such that this angle plus this angle should add up and make the entire angle. That's called the angle addition postulate. See how it looks like segment addition postulate, but we're just dealing with angles. So it's over here on the left-hand side, friends. If B is on the inside of AOC, then the measure, notice I'm using M because we're talking about measures, the numbers. The measure of angle AOB plus the measure of angle BOC is equal to the measure of the entire angle. So just like we did in segments, when we talked about segments, we talked about them being congruent. We talked about using the little notation on top. But if I'm just talking about the length of it or the number, we didn't put the notation on top. Same thing with angles. If I'm just talking about what is angle AOB, the actual angle itself, or what's the measure of angle AOB, I put the M in front to mean the measure, the actual number. I like this one over here. This is kind of neat because if I take these 2 angles and I paste them together, they actually make a straight line. If I take this angle plus this angle, by the angle addition postulate, we should get the entire angle, AOC, which again is a straight line. It's a straight angle. But because they both add up to make a line, they're 2 angles that make a line. They're called a linear pair. 2 angles that are adjacent to each other that add up to a full 180. That makes a postulate. The postulate is called the LPP, the linear pair postulate. If 2 angles make a linear pair, then their measures add up to 180 degrees. That just makes sense by looking at it too, right? These are 2 linear pairs, and back to back they make a straight angle, so they must add up to 180 degrees. It just makes sense. But now I'm going back to the idea of what if we had our protractor and we wanted to find the measure of, say, this angle here, which would be QOP. What is the measure of angle QOP or POQ? That's hard because before, when we had angles that were off here on the sides or over here on the sides, we could just start at 0 and count. Over here, using the inner numbers, I could 0 and count. But when you're off here in the middle, that's a little bit harder. Maybe we can figure it out. It looks like the ray OP is going through, oh gosh, that's maybe like 135 degrees if I'm using the outer numbers. And therefore, OQ, if I use the outer numbers, looks like it's going through, well, 90 right at it. So I'm traveling from 90 to 135. How far did I travel? From 90 to 135, oh, that's, I think, about 45 degrees. And we'd be right. And if we want to, we can actually take the inner numbers if we want instead and use these. Let's see what happens. Over here, it looks like the inner number here is about 45 degrees. And over here, the inner number is, again, 90 degrees. But since the inner numbers go in this direction, how far do I travel to go from 45 to 90? Again, 45 degrees. So there's a cool way of doing this. In terms of, if you know where the X ray is and the Y ray, how can we use those numbers to always find the measure of the angle? And that's what's called the protractor postulate. Now it looks a little strange up here because I grayed out a version that's not really important in geometry anymore. So you can see it visually, but you can completely ignore it. The idea is when you're trying to measure an angle, and one ray is a certain measure, and the other ray is another measure, to find the actual angle measure, we can take one number minus the other one and take the absolute value. Sounds a lot like the segment postulate, the ruler postulate that we did with finding coordinate points on a number line and finding the distance. It's the same idea. So this is great. So I can go in any direction I want and I'll still get the right answer as long as I take the absolute value. So if you go back to POQ again, use the same numbers. It doesn't matter which way you go. I can say the measure is going to be 90 minus 135, but I'm taking the absolute value. And the absolute value here of negative 45 would be 45. So whichever direction you want to go, it's fine as long as you include the absolute value. So subtract the two angle numbers and take the absolute value. All right, segments can be congruent. Well, angles can be congruent as well. Congruent angles have, again, the same measure. They're both 20 degrees, or they're both 35 degrees. They are congruent. And here we can say, well, notice that there's only one letter on each one. So in fact, we could actually call this one angle R. And that would refer to that angle because we're just referring it to its own vertex. This would be angle angle S. Well, if these are congruent, let's say that angle R, let's use our congruent symbol, is congruent to angle S. And that's how we would do that. We can also use, remember we use little tick marks, red tick marks for segments. We can do this with our angles. If I do this and this, that assumes that angle R is congruent to angle S. Just like with segments, if I have another pair of angles and I want to show those are congruent as well, we would just increase the number of little curved marks that we make. Just like we would use 2 tick marks for a different pair of segments. And also just remember, when we're talking about the angles themselves, they are congruent. If we're talking about the measures are numbers, and numbers are never congruent. Numbers are equal. It's shapes that are congruent. So both these mean the same thing, but just notice how important the notation really is. All right, those are congruent angles. They have the same measure. I can have adjacent angles, and adjacent we know from English just means sort of next to. But in order to be adjacent angles, we need a couple rules here. Okay, ready? Rule number 1, in order to be an adjacent angle, to be an adjacent angle, they need to share the same vertex. That's rule number 1 for the adjacent angle club. Okay, second of all, they need to share the same ray. A lot of times that ray is sort of in the middle, although it's hard to kind of explain that. We'll see in a couple examples. And finally, there can be no points inside one angle that's also inside the other angle. Okay, those are the 3 rules to be an adjacent angle. Let's go through some of these 5 pictures up here that you see, and let's see if they belong to the adjacent angle club. And if they don't, let's figure out which rule they're breaking. All right, let's start with the left one over here. Angle 1 and angle 2, are they adjacent? Let's check the rules. Do they share the same vertex? Yes, they do, right here. Good. Do they share the same ray? Yes, they do, right here in the middle, folks. This is the same ray that they're both sharing. So check. And are there any points that's inside one angle, for example here, 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 that will ever be inside the other angle? No, there's no way, because angle 1 is sort of on the left side of angle 2, so none of the points in angle 1 can ever be in angle 2. So, yes, that's good. No points inside one are also going to be inside the other. So is this one adjacent angles? Yes. Yay. All right, number 2 over here. Are these adjacent angles? All right, go through the checklist. Do they share the same vertex? Yes. Do they share the same ray? Yes. And are any points inside the interior of one angle also inside the interior of the other angle? No. So that's good. These are also adjacent. Okay, let's find out why these 3 are bad. Which rule are they breaking? Number 1, 2, or 3? Let's take this first one over here on the left. All right, do they share the same vertex? Yes. Angle 3 and angle 4 are the same vertex. Do they share the same ray? No. Notice that angle 3 is made up of these 2 rays, and angle 4 is made up of these 2 rays. So they do not share the same rays. So these are not adjacent angles. Let's try this one over here. It's just weird looking. All right, first of all, do they share the same vertex? No! Wow, they broke the rule right away. Here's the vertex of 3, here's the vertex of 4, and that's not the same. So definitely not adjacent. Okay, how about the last one? This one here. Are these adjacent angles? Okay, do they share the same vertex? Yes, they do. Remember, this notation here is saying that this whole thing is angle 4, the big outside angle. And the vertex of the outside angle is there, and the vertex of 3 is also there. So they share the same vertex. Check. Do they share the same ray? Yeah, they do. Angle 3 has this ray that's also on angle 4. So yes, they do share it. It's not in the middle, though. We talked about that before. And here's how we're going to break the final rule. Are there any points that are inside one angle that are also inside the other angle? Yes. If I take a couple of these points here that I put inside angle 3, can you see that they're also inside angle 4? And because they're inside the interior of another angle, they break that last rule. These are not adjacent. They're kind of overlapping, right? So this last one's not adjacent pair. So these are your 3 rules, folks, of how to make adjacent angles. Last time we were able to bisect a segment. Remember, we bisect a segment with another ray, or a plane, or a line, or a segment. If I want to bisect an angle, that means I do want to sort of divide it into 2 congruent angles. So maybe like, I'm going to start at Y here. Try to make it right in the middle if I can. All right. There's my bisector. I just bisected an angle. And by doing that, I made this angle is congruent to this angle. Why don't we call this point here A? So we can therefore say that angle XYA is congruent to angle ZYA. Good. So my bisector here would be YA. But what is it? What is YA? Look at the shape of it. It's a ray. So generally, the bisector of an angle is almost always a ray. Not usually a plane or a segment or a line. It's usually a ray. And it bisects the angle into 2 congruent angles. That makes sense. So now this one could be, for example, 20 degrees. And this one will also be 20 degrees. And by angle addition postulate, it means the whole thing would be about 40 degrees. Now, we got to be careful. Geometry is all about looking at shapes. And we can't assume everything that we see with our eyes. So I ask you, what can you conclude with this picture? When you look at this, is there anything that you know for sure? For example, could you say that angle DBE is an acute angle? Sure. Could you say that angle ABC is a straight angle? Sure. What else could we say? How about angle DBC? What kind of angle would that be? It looks bigger than 90, but less than an 80, so that's definitely obtuse. But here's my question for you. Do we know for sure if this is a right angle? Like, do we really know for sure? And we can't always assume, and that's the point. Don't always assume. Right angles. And what we'll do to show a right angle is we'll put this cool little box. Look at this. And whenever you see a box inside an angle like that, that's a right angle. There's your 90 degrees. Okay? If you don't see that, don't assume it is 90. Let them tell you, let them show you before you assume. If it doesn't say it, you can't say it. If it doesn't show the box, you don't know if it's 90 degrees. So just be really careful with that, folks. All right, finally, for the end of this lesson, let's just do a couple practice problems. Look at this beautiful picture with A, B, C, D, and E. We have lots of numbers here for the angles. We have lots of letters. Ooh, we have a cool little box here. Do you see that? Neat. All right. Why don't you try to pause the video and try some of these examples for yourself. For number one, you're going to try to find the vertex point of angle 3. You're going to try to find a right angle. And then give me another name for each of the numbered angles using 3 letters if you can. All right, we'll see you soon. All right, number one. Let's find angle 3. Angle 3 is over here, which is made up of E, B, D. You notice how I said that? I said E, B, D, and the vertex letter is always in the middle, so the vertex would be point B. All right, let's see if we can find a right angle here. Ooh, I saw that box. Do you see that? This is your box, which means this is your right angle. So let's see, let's name that. We can call that many things. You have a point B up here, you have a point E, you have a point D, you also have point C if you extend it. So there's actually a lot of ways you can say it, and all these are right. You could say angle BED. That's the right angle. Or you can actually say angle BEC, because B to E to C also forms a right angle. Now that assumes also you can go backwards. You can say DEB, CEB, or could we just call it angle 8? And that's also good too. So all 3 are the right angles, and we know that because of the box. All right, let's try each of these angles we have here. How about angle 1? Angle 1 over here. All right, that's right at the vertex, so I can call that, how about angle BAE is good. Or do you see that after A to the right, that extends for a long time. So I'm going to erase that, and I could say BAE. How about BAD is also good. And you could also have said angle BAC. That's also fine. And of course, all the reverses are good too. And because A is all by itself, you actually could call angle 1 the same thing as angle A and just call it by its vertex, because that doesn't mean any other angle except angle 1. Okay, let's try angle 6 over here. Angle 6. Can we name that? Angle 6 over here? All right, I could call that, how about angle BDC? Or backwards, CDB. And that's it. I can't call angle BDC or angle 6, I can't just call it angle D. Even though that is the vertex, I can't say this is angle D. And the reason is, D is also being used for another angle over here. So really, if you said angle D, Mr. Brown, I'd say, well, which one do you mean? The one on the left or one on the right? So we can only use the vertex letter if that angle is all by itself and not shared by anyone else. So the only answer to that one could be either angle BDC or angle CDB. How about number 5? Angle 3, way up here. Oh, okay. How about I call it angle EBD, or the reverse of angle DBE. And that's it. We can't call that one angle B also, because which angle does that mean? There's so many overlapping ones there. How about number 6? Angle 4. Angle 4 up here. Let's see, I could call that one angle CBD. or again the reverse. Can't call it angle B though. Okay, how about angle 7 for number 7 over here? Angle 7 we could call, how about angle BD is the vertex, E. Or do you notice that that ray of DE goes on a little bit longer, so I can call it actually angle BDA is also legit as well, or angle 7. Can't call it angle D though. Okay, how about angle 2 here? Angle 2 up here, did you call this one angle ABE or EBA? And that's it. Number 9, angle 5 over here. All right, we've got a couple choices here. Ready? We've got angle BCD. Did you get that? Or angle BCE, because that makes the same angle of angle 5. Or how about this? Angle BCA. Or because C is by itself, we could call that angle C. It's legit here. The vertex point of C is all by himself, so it's okay. Or, of course, all these letters backwards would be fine too. DCB, ECB, and ACB. All right. What's next? How about angle 9? Over here. Okay, I would call this one angle BEA or AEB, backwards, but not angle E. Would not make sense. And there you go, friends. That's how you're naming angles. That's how we identify them. That's how we measure them. Good work today.